Up until now, I've focused on the metric equation in just one dimension, so it would be c times delta t squared minus just delta x squared. But if I want to generalize to 3 dimensions, it's really quite straightforward. I just replace delta x squared by the entire distance squared. Delta x squared plus delta y squared plus delta z squared. We can sometimes write this as delta r squared. Notice the entire space-time interval has the time component and the 3 spatial components, and the only difference between time and space is that whereas we're adding the time part, we're subtracting the space ones. If I want a space-like time interval and I want to keep it positive, I switch it around. I add the space-like and subtract the time-like. A lot of texts will simply call this a general delta S squared, and it's the invariant interval squared. They'll pick one of these two definitions. It doesn't really matter which. And then they'll just say, if we pick the top definition, it's positive for time-like, 0 for light-like, and negative for space-like. If they choose this to be their fundamental definition, then it's positive for space-like, 0 for time-like, and negative, 0 for light-like, and negative for time-like. But all the basic results we've had still come through. In the energy part, we still have e squared minus, now it's the vector momentum squared c squared. And that's always equal to m squared c to the 4th. And that's invariant. A point here, in the example I worked, this was not a single mass. I had multiple particles going into my E and P, my energy and momentum. But this quantity is still an invariant, even when we're not talking about a single particle.